Good morning, everybody. All right, can I have some indication that you hear me? And can you hear me now? Hello?
I can hear you, Professor.
All right, thank you. Appreciate it. All right. Yeah, we'll get started in a couple of minutes here. All right, it's 10 o'clock. We'll get started. Thanks for coming here today. All right, so we're looking at Module 6. We're starting out with the balancing of chemical reactions. This is something that's probably best just done by practicing. I do have examples in Module 6, of course, but also we've got this situation down here, this interactive exercise, which I think is really good practice. And what this allows you to do is practice the kind of problems that you would end up seeing, say, on the test, where we're interested in the sum of coefficients. So looking at something like what you're seeing here, you see all these numbers here. These numbers represent all the coefficients added together once it has been balanced. So I'm just going to do a couple of examples here just to give you an idea so that you can see what I mean by sum of coefficients as well. There is a video at the very beginning of the video tutorials that tells you what sum of coefficients means, but let's have a look. We'll look at number 2 here, the second one. So V2O5 plus Ca gives CaO plus V. The idea of balancing, of course, is to make sure that all the elements on both sides of the equation had the same number of elements. So we've got V2O5, that means there's two V's, and I could balance those two V's by putting a 2 in front like that. So by balancing, we're allowed to change the number of moles of things. I couldn't change this to V2, but I can put a 2 out in front and have two separate V's to balance that. You'll notice that there's 5 O's, and I can balance those by putting a 5 out in front of the CA. That, of course, changes the CA and forces me to put a 5 in front of there. Let me move that over a little bit. Sorry, I didn't mean to do that. Here. This thing's going to give me trouble moving it. Okay, there we go. Just looking for my palette here. Put this plus sign too close to the CA. There we go. So we can put a 5 in front of the CA like that. Now, if I want to find out the sum of coefficients, what you've got to remember is that if there's nothing out the front of something, then you immediately assume that it's 1. So if I was looking at the sum of coefficients, it would be 1 plus 5 plus 5 plus 2, which is 13. And that would be the answer that I would select from down here. You can see the 13 here, and I would just drag it up and put it here. So that's good practice. I do like that exercise. Those examples are fairly similar to the kinds of examples you might see on a test as well. Does anybody have any questions about balancing here and what sum coefficients means? Okay. So again, I didn't want to spend too much time on balancing, but the rules are as follows. You can only balance something by putting a number out in front and treat it as a dynamic process, because as you make changes to one compound, it probably means you have to make changes to something else on the other side of the equation. And I guess the only way you can really get a handle on this is just to practice it. So the next part is, this is stuff I really want to focus on, because this is what people have a lot of difficulty with, is predicting the products of reactions, especially these double displacement reactions and reactions of acids and bases. This tends to be very troublesome for a lot of students. So when we're looking at something like an acid-base reaction, the usual form is we have an acid, we have a base, which gives us salt. And by salt, I'm talking about not necessarily sodium chloride, but pretty much anything that's an ionic compound is considered a salt, and water as a product. And the reasoning here is that acids, as you can see here, form H plus when dissolved in water, while bases form OH minus when dissolved in water. So of course, when you take H plus and OH minus and you join them together, what do you get? Well, you get water. So H plus OH minus gives H2O. So that's going to form the foundation of our acid-base process. So what kinds of compounds are considered acids? Well, anything with an H plus as the cation is going to be an acid. Sometimes we can have the H in the middle here, because those are still considered acids as well. And then we've got something like, say, sodium hydroxide or calcium hydroxide, where you can see the OH. So anything that forms OH negative when you stick it in water, that's going to be a base. So being able to identify the acids and bases is a good start to being able to do these kinds of problems. So let's look at an example here, and this is the example I have in the soft chalk. The order of these is not important. I could put the acid first or the base first. It really doesn't matter. In this case, the NaOH is the base. And what I like to start with is by drawing out a picture. So the NaOH would be drawn out as Na plus and OH minus. Now, how do I know the charge on OH minus? Well, we can get that off the polyatomic ion sheet, which you'll have in front of you. You don't have to memorize that. And we're using a lot of the same concepts as we used in Module 5, like having to have the charges match, for example. So if the OH is negative, it means the Na has to be positive. The H2SO4, if I drew that out as a picture, again, the charge on the SO4 can be gained from the polyatomic ion sheet. That's 2 negative, and each of these H's will be 1 plus. So already you can begin to see how this is going to play out. The reaction itself is called a double displacement, which means that the cation of one side will join to the anion of the other side. Think of it like two couples dancing, and they of the opposite sex, and they switch partners. Think of it like that. So male, female, male, female. This male joins with this female. This male joins with this female over here. Think of it like that. So what we know is that the Na plus will join with the SO4 2 minus, and the H plus will join with the OH minus. A really important point here, though, is that we're only considering what happens with one of each of these. One of the biggest points of confusion that this produces is the fact that it seems like I'm ignoring this poor H plus down here, not taking it into account. In reality, what I'm doing is I'm just trying to figure out what the compounds are on this side, and then I'll handle the balancing later. And in this instance, I know the H plus and the OH minus join together to give water. I'll just put that over here. Again, it doesn't matter where you put it on each side of the arrow, so it's going to be plus water. And I know that the Na plus will join with the SO4 2 minus. So you'll notice I did ignore that H plus there, but that's fine because what I'm interested in is trying to figure out what the products look like first before I do any balancing. So I look at the Na plus SO4 2 minus, and I know that it needs to be Na2 SO4. The reason for that is because I'd be asking myself the question, well, how many of each do I need to make that balance out? So I need to have the positives match the negatives in every single case, plus water. So there's the other point of confusion. People wonder, well, look, how can you just pull a sodium out of the air? How can you just add a sodium to that compound? It certainly doesn't seem like you have enough sodiums over here to do that. Well, we're going to take care of all of that later. Our first priority is figuring out what the balanced compounds are before we go ahead and balance the equation. So the answer to this, the compound that we get is Na2SO4. And then we could, if we wanted to, balance this, and we would do that by putting a 2 in front of the NaOH over here and a 2 in front of the water. And then that would balance the equation. At that point, then we've taken care of everything. But again, let me summarize exactly what I did here. I drew pictures of the acid and base. I then took one of each on each side to try and figure out what was going to join with what. I then balanced the resulting compounds and then balanced the equation. And that's the way you do it. So often I'll see people say, well, look, there's two H pluses here and then no H minus. Doesn't that join together to give H3O or something like that? No, it doesn't. It joins together to give water. Does anybody have any questions? Okay. Well, how do we handle one now where the H is kind of in the middle of the compound? So this is the acid because it's got the H in the middle here, and we know this is the base because it's got the OH here. So if I drew a picture of this, I'd want to draw a picture so that the H plus came out. And I'd know to do this because in these kinds of problems, I'm told that, or on the test at least, that it is an acid-base problem. So I know I need to focus on finding out where the H pluses are and where the OH minuses are. The rest of this, I have Ca2 plus and CO3 2 minus here as well. And you can see that we'd actually have 2 H pluses and 2 CO3 2 minuses. So we know that the H plus and the OH minus join together to give the water. And then we know that the Ca2 plus will join with, and it doesn't matter, just one of these, CO3 2 minus. That gives us our compound. So we have Ca, whoops, let's put the charges on here, Ca2 plus, CO3 2 minus, plus water. And that will join together to give CaCO3. It's our compound. And then we can balance it. So our time was initially spent there trying to figure out where the H plus came from and where the OH minus was going to come from to form the water. So it'd be CaCO3 as a product plus water. And to balance this, I need to put a 2 in front of the Ca. And I think a 2 in front of the water, that will balance it out. So that would be the final equation there. So those are a little bit more difficult when you have to have the hydrogen in the middle. You have to figure out where it's going. You might be able, well, how do you know where it's going to go? Well, it's an acid-base reaction. So we know it has to be H plus reacting with OH minus. And then the rest of whatever else is left over joins together to form a compound that balances out. And that's always going to be the focus at the beginning of the problem. Does anybody have any questions? Now, balancing these hydrocarbon reactions is not incredibly difficult. The product of a hydrocarbon reaction, you can imagine this as being what runs your car. The hydrocarbon is a gasoline and it reacts with oxygen in the air to form carbon dioxide and water. And that's exactly what happens in your car to make it run. And this obviously produces heat, which allows for and energy for the pistons to go up and down in your car. And that's how it works. So I've got CXHY, that could be any hydrocarbon, so any combination of carbon and hydrogen here. I'm going to show you 2 examples here. The first one is C4H8 plus O2. Gives CO2 plus H2O. Now you're always told this, so you don't have to memorize this. Now to balance this, we balance the carbons first by putting a 4 out the front. Then we balance the hydrogens, and I'll do that by putting a 4 out the front. That gives me the 8 that I need here. So that's a 2 there. The next thing, this is the hardest part, is balancing the oxygens, because on this side I've got 8 and 4 is 12, which means I need a 6 in front of here to balance that. And that would give me 12 on this side as well. So that one's not too bad. If I wanted to do the sum of coefficients, it'd be 1 plus 6 plus 4 plus 4, which would be 15. Does anybody have any questions about balancing that first reaction? The next one, sorry, go on, yeah.
So the 15, when you add in all the coefficients, like I saw a problem on the module 6, and it was like I would have to balance it, but like the numbers that I used to balance, I didn't like I don't know. I didn't know if I put the number that I balance with or like the number of the coefficients.
No, just the coefficients, whatever you get at the end. So here, we assume that's a 1 because there's nothing in front. And
Okay.
there's just 1 plus 6 plus 4 plus 4. Whatever you have at the end once it's balanced.
Okay. All right. I see it.
Okay.
Thank you.
This next one is a little bit more complicated. Now we're going to follow the same pattern initially with how we balance this. So we'll put a 6 in front of the CO2 like that. That's okay. Then we put a 3 in front of the H2O. That balances the hydrogens. Then we need to balance the oxygens, and this is where things get a little bit more dicey. On this side, I have 6 times 2 is 12, and now I've got 3 oxygens here, that's 15. So to balance this, what I'm going to do is instead of 15, of course, I'll put 15 over 2. So 7.5 O2s essentially. So that necessitates multiplying everything by 2. So I'll end up with 2 C6H6 plus 15 O2, which gives 12 CO2 plus 6 H2O. Now the reason I have to do that is because we can't be left with fractions as coefficients, so we have to multiply everything by 2 in that instance. There's an easy way of knowing by looking at a problem whether or not you're going to have to multiply by 2 during the course of that problem. And what you would do is you look at the number of hydrogens in the initial problem, and you divide that by 2 and you ask yourself, is that going to be odd or even? So if you take 8 divided by 2, you get 4. That's an even number. But in part B there, problem B, 6 divided by 2 is 3, which is an odd number. So that tells me I know that I'm going to have to end up multiplying by 2 in order to get that final equation right. Okay, does anybody have any questions about hydrocarbon balance? So I do like this interactive exercise in the soft chalk as well. Take a look at these and see if you can determine whether you're going to have to multiply by 2 or not. All right, so look at C7H8. What do you think? Do you think you have to multiply it by 2 or not? Once you balance it. Any thoughts? Nobody has any thoughts? Okay. So 8 divided by 2 is 4. That's an even number, so no, I'm not going to have to multiply by 2. This one here, 12 divided by 2 is 6. That's an even number, so no, I'm not going to have to multiply that by 2 either. Again, 8 divided by 2 is 4. So no multiplication. This one here, 10 divided by 2 is 5. Yes, I will have to multiply this one. C6H6, 6 divided by 2 is 3. Yes, I will have to multiply that one by 2. 10 divided by 2 is 5. Yes, I have to multiply that one by 2. And 14 divided by 2 is 7. I have to multiply that one by 2 as well. So you can imagine that by multiplying the whole reaction by 2, it does increase the sum of coefficients quite dramatically. And in this instance, it would be 17 plus 12 is 29, and 6 is 35. So that would be my answer there. 35 would be the sum of coefficients. All right, any questions? Nobody has any questions, huh? Now these next ones are somewhat difficult, the double displacements. And the double displacements are really an extension of the acid-base reactions we've just been looking at. So I'm going to do this by way of an example, and we're actually going to do three things. Whoops, sorry. We're going to do three things with this. We're going to balance and predict the products of the reaction first. Then we're going to write the full ionic equation, and then we're going to write the net ionic equation. You'll notice they have little AQs next to them. That means they're aqueous solutions. What's going to happen here is that we're going to have two solutions that don't have anything in them. I mean, well, they don't have any solids or anything. I mean, if you look at them, they'll just be like clear liquids with nothing in them. Then we add them together, and what's going to happen is we're going to end up with a situation where we've got the liquids added together, but we're also going to have a whole bunch of solid here, which will end up sticking to the bottom. So we end up getting what's called a precipitate. So that solid there is called a precipitate. So these would be aqueous, and that's where the AQ comes into play. And then the precipitate there is solid. Any questions so far? So what I like to do is, again, I'm kind of obsessed with this. I like to draw out these pictures of things so I know what I'm doing. So it'll be PB would be two NO3s, and the NO3s have a -1 charge, which means the PB has a 2+ charge. Does anybody have any questions so far about anything I've done? I did the same thing with the Na3PO4. It looks like somebody's got a question here. Let me see what the chat has to say. Oh, okay. So that'd be 3 Na pluses and PO4 3 minus. Again, the 3 minus we can get off the polyatomic ion sheet, which you'll have. Now I said this was double displacement, which means that it's going to follow the same pattern as what we saw earlier. We know that the PB2 plus will join with the PO4 3 minus. And we know that the Na plus will join with the NO3 minus. Notice again how I only took one of each. I didn't take all of them. That usually annoys students greatly because they're thinking, well, how can you just ignore all those other Na pluses and NO3 minus? How do you justify that? Again, what I'm trying to do is I'm trying to figure out what the compounds are first before I do any balancing. So I have to balance the compounds before I balance the reaction. I'll say it again. I have to balance the compounds before I balance the reaction. If I'm balancing the PB2 plus and the PO4 3 minus, I'm going to be using a lot of the same techniques as we talked about back in module 5. But to make that compound, what I'm saying to myself is, well, how many of each do I need to make those positives and negatives balance out? So I need 3 2 pluses to give me 6 plus and 2 3 minuses to give me -6. And then we'll have NO3 over here. Na plus NO3 minus joins together to give NaNO3. So that's how I'm going to come up with the compounds. Now that's not quite balanced yet. balance the compounds and balance the reaction. It's always the way we're going to do this. Now, I had said earlier what these were. This is an aqueous solution, aqueous. But you'll remember I said that one of these is going to come out to be a solid. Now, I'm not sure which until I look at my friend, the solubility chart. The solubility chart allows us to look at combinations of positive and negative ions and to be able to see whether or not we're going to get a precipitate out of them. In accordance with the key, AQ is aqueous, which means no precipitate. The I means insoluble or partially soluble, which means we're going to get a solid there. So that's why you'll see here combinations, you'll see AQs, you'll see Is. So for this one, we have PB and we have phosphate. So I find lead and then I find phosphate, which is over here. And then I run up the table here and I come up with an I. So I know that the solid that's going to come out of this will be the lead phosphate. And then the AQ will be for the sodium and the nitrate. And you'll see that that's going to be AQ over here, sodium and nitrate says AQ. All right, any questions so far? That's not quite balanced. Let's balance it. Let's see how we might do that. We've got PB, we've got 3 over here, we've got 1 over here. So I'm going to put a 3 in front of the PB on this side. But that gives me 6 NO3s. So I need to put a 6 in front of the NaNO3 over here. And I still have 2 phosphates on this side, so I put a 2 in front of the Na3PO4. So you'll notice that gives me 6 NAs, which matches the 6 NAs I have over here. So that would be the complete balanced equation. All right, I'm going to stop there for a second. Does anybody have any questions? So that would be what I'm calling part A of this process, which would be balancing and predicting the products of the Na3PO4. The next thing we want to do is be able to write a full ionic equation. Well, you've got to understand what ions are. Ions are charged particles. And when you've got an aqueous solution, what it is, it's just the ions in solution. And that's it. I mean, it just breaks apart into those ions. So how do we know what this is breaking apart into? Well, what I like to do is I like to, I've got a 3 outside. It's kind of like a box that contains PB and 2 NO3s. That's minus, minus, and that's going to be 2 plus over here. And then we'll have another box that contains, well, 2 boxes actually. So I'm putting 2 out the front here. That contains Na, and PO4, Na plus. And you might be wondering, well, do you have to put the charges on? Well, the thing is, it's a full ionic equation. So yes, you do have to put the charges on. Now the PB3PO42 is a solid. It doesn't break apart in solution because it's a solid. So I'm just going to leave it the way it is. And then we'll have another 6 boxes here. So somebody's got a question, which I'll come up with in a second. That contains Na plus and NO3 minus. Okay, let me see what the question was here. Is this recorded? Yes, it will be. It is recorded. Looks like it's recording here, so I think we're in good shape. All right, does anybody have any questions up to this point? So to write out the full ionic equation, I have to count up how many of everything that I have. I have 3 Pb2 pluses. I have 6 NO3 minuses. I have 6 Na pluses. And I have 2 PO43 minuses. All right, I'm going to stop here for a second. Does anybody have any trouble seeing where I'm getting those numbers from? 3, the 6, the 6 and the 2. All right. You know, if nobody's going to say anything, I'm just going to assume you're understanding. You know, that's the thing. I mean, there's 2 possibilities here. Either you all understand what's going on, or you are all so lost that you have no idea what to ask. And that's not a good situation if that's true. But I don't know, because nobody said anything. So, I mean, that's all I can do. All I can do is just keep going. And the solid, we just leave as it is. And then the 6Na plus 6NO3 minus is what we'll have from the 6NaNO3. So that there is what's called the full ionic equation, what I just did. All right, let's see. So there's a chat here. What have we got? All right. Does anybody have any questions about the full ionic equation here? Now, the full ionic equation, you can see that it's got things that are the same on each side. So we've got the 6 nitrates, that's the same. 6 Na pluses, that's the same. These guys are called spectator ions. They're called spectators because it's of the appearance that they don't interact or they don't change during the reaction. As such, we can get rid of them and we can write what's called a net ionic equation. So just like we would in a regular algebraic equation, we can remove like terms from each side and we are left with the net. And what you'll see or what you'll observe once we do this, to put it in real simple terms, what we've done is simply shown what's forming the solid. So everything else that's soluble gets thrown out. Only the stuff that's forming the solid is what we're considering. So the 6 Na pluses and 6 NO3 minuses are gone. So this bottom one here, this is the net ionic equation. Does anybody have any questions? Okay, thank you. If I want to come up with the sum of coefficients for the full ionic equation, it would be 3 plus 6 plus 6 plus 2, which would be 17, 18 for the PB3PO42, and then plus 6 plus 6. So that would be 30, would be the sum of coefficients. For the net, it would be 3 plus 2 plus 1, which is 6. Just squeeze that in down here. So that's how it's going to be on the test as well. I'm going to give you a reaction. I'm going to ask you what the sum of coefficients of the full ionic and the net ionic equations are. And you'll have to figure that out. All right, does anybody have any questions? Okay. So there's a number of interactive exercises here that are fantastic practice for figuring out the compounds that we're getting as products. The first one. The next one is about the sum of coefficients, the full ionic reaction. That's really good practice. And the last one here, the sum of coefficients of the net ionic equation. So, you know, you've got plenty of stuff here. The other thing, and this is what's really cool, is if you're having trouble with these exercises, I have videos linked for each of them. Videos linked to that are specific to these actual activities. And you can watch those videos if you're having trouble with them. I think these are fantastic practice, but barely anybody ever does them. And then, you know, it's those same people who I hear from later saying, oh, you know, this is such a hard exercise. Well, and then they didn't do anything. They didn't do the work I told them to do. You know, and that's what's so frustrating. Because if you do the work and you understand the examples, then, you know, it's fine, it's easy. But if you don't do that, then it's going to be very difficult. You know, it's all about how much time you'll want to put into it. I do appreciate you guys being here. There's how many of you? 9 here today. You know, I do appreciate you putting this time in. I know that some of you will watch this later, and that's okay too. But I know I'm going to also have people who don't do it. Okay. What else have we got here? Decomposition reactions. So decompositions, we've got 2 examples here that we're going to be talking about. Well, 3, I suppose, but we've got chlorates and we've got hydrates. We'll do the hydrates first. The hydrates are pretty easy. And hydrates have this kind of formula. So this would be Na2CO3, and then you've got this dot here, and this one would be 10H2O. So what this is it's 10 waters of crystallization. So when this crystallizes, you get 10 molecules of water. That dot there is not multiplication or anything else. It's a very simple decomposition process. What we get is Na2CO3 plus 10 waters. So this is called, this is called a hydrate. And this here is called an anhydrous salt. The prefix "an" means without. So it means the salt without the water. So what usually happens is we're heating this. And when we heat it, we end up with the salt and the water comes off as steam and it never goes back and adds back to be Na2CO3. So these 2 things are different. In fact, when we've got the copper hydrate is blue and the anhydrous salt is white. So you can actually see the difference there. I think these guys are both white, so you wouldn't really see too much difference in those. But you'd certainly see a difference in the masses, because once the water was gone, the mass would go down. So that's for hydrates. And then we've got the chlorates and the perchlorates. Now, when those decompose, they always decompose into X and Cl plus oxygen gas. So that's always how it goes down. But we need to be able to figure out the charge on the X group here. And the charge doesn't change. So this would be, if I drew a picture of it, it would be X plus and ClO3 minus. The X here doesn't really matter what it is. I'm just doing this by way of explanation, just to illustrate what's going on. So we'd end up with X plus and Cl minus, because we know that this is the -1 of the polyatomic ion sheet, which means X has to be plus. And if I join these two together, it's going to be XCl. So to finish up balancing that, you can see that the X's and the Cl's are balanced, but the 3 oxygens on this side, 2 oxygens on this side, that's not balanced. But I can balance it by putting a 2 in front of here to get 6 and 3 in front of here to get 6. So it's kind of like balancing half and a third and trying to add them together by using common denominators. And if I do that, then I need to put a 2 in front of the XCl to balance that out. Give you another example here. So what if you had XClO34? Now what you'd have then would be X4 plus and Cl minus plus O2. These guys were joined together to give XCl4. And again, it doesn't matter what the X is, but I can automatically know the charge because I know that ClO3 has a -1 charge. So it'd be XCl4 plus O2, and then I can balance it. Let's see, so we've got 4 Cl's already, that's fine. We've got 1 X, that's okay. The oxygens, we've got 12 on this side, which means I need to put a 6 in front of here. And then that would be balanced. And the perchlorates, the ClO4 compounds, they balance in the same way. But the key there is figuring out the charge on the cation. Once we know that, and it's easy because the charge is always going to be equal to the number of chlorates or perchlorates that you have connected to it or with it. Does anybody have any questions? So I've got up here, this is always the way that these perchlorates and chlorates will decompose. They decompose into the chloride and oxygen gas. Always, that's how I go. And the hydrates always decompose into the anhydrous salt and H2O. That's it. Does anybody have any questions? Again, I go through examples of those here as well. Plus, I've got these interactive exercises that have video explanations that go along with them as well. I think this is the last section, is the single displacement, yeah. Okay. Now, with the single displacement process, what you're looking at is the reaction of something solid that isn't charged with something that's aqueous that is charged, and then things switching around. So you can see the Ca solid actually replaces the copper, and the copper becomes solid. So the Ca becomes essentially Ca2 plus, and the copper 2 plus becomes copper solid. That's going to be the way that the reaction goes. Now, whether the reaction goes or not is going to be determined by something we call activity. And another way you can think of it is reactivity. So as long as the solid here is more active or more reactive than the cation here, then the reaction will go. And then if that's not true, then the reaction doesn't go. So that's the rule here. Let's see if I've got it here. So first of all, we have to be able to identify the solid or neutral and the cation. Excuse me, let me turn this down. Sorry about that, I just had to mute my phone. Okay, so we have to be able to identify what the neutral compound is and what the cation is so we can make this determination. So it's always something that looks like this. We'll say, we'll do this. So AB will be aqueous, C will be solid, CB will be aqueous, and A will be solid. And I often consider this to be neutral because it doesn't have a charge on it. And the A here is going to be a cation. So you'll notice that during the process, the C becomes the cation and the A becomes neutral. All I want you to be able to do at this point is look at the compounds on the reactant side, like we have here, and just be able to determine which one is neutral and which one's the cation. So you can see the solid is always neutral and the one that's aqueous is always going to be the cation. From there, then we can more easily understand what this statement means here. If an element is more active than the cation of the other element, in other words, in this case, to say that if C, which is the neutral one, is more active than A, then the reaction will proceed. If A is more active than C, reaction does not go. It really is that simple. So it's all about whether A is more active than C. So how do we know that? Well, we could do that by looking at what I'm calling an activity series. This tells you what's more active than whatever else is around. This is all based on what we call standard electrode potentials. And oxidation reduction processes, which is something that you'll see in Chem 2 if you go that far. But we actually don't use the activity series in the problems that we talk about that relate to single displacement. What we do is I'll show you the example. That's probably the best way of explaining this. I'm going to pull up an example from the test here, from test 2. And here. Okay, so here's an example. So this is a single displacement. And what I have here is the experiment, which gives you the neutral and the cation. So you can see the neutral would be Fe and the cation here would be Cu. The observation here will tell you whether or not a reaction occurred. So anything in here that indicates that a reaction occurred will tell you that yes, a reaction occurred. If you see the words no reaction or no change, then that would indicate no reaction occurred. And it's actually the knowledge of whether a reaction occurred or not that tells us which one is more active. So we're still using this thing that I have up here. I just want to be able to show the whole thing here, which it won't allow me to do. And let me see if I can push it down here, perhaps. There we go. And it gives you the instructions to actually solve the problem here. So if you're looking at this one, it says coating forms on Fe surface. So the answer here would be, in this case, yes, for whether a reaction occurred. Remember, if it says no change, so 1 would be yes. If it said no change, then the answer would be no. The neutral element, well, that's going to be the Fe. The cation, that's going to be the Cu. Cu2 plus specifically. And then you can figure out which one was more active. So what we're using here is the knowledge that a reaction actually occurred. So we're looking at this, say, well, what's more active if the reaction goes? Well, according to this, the neutral one is going to be more active, which would mean that the answer to number 4, the more active one is going to be Fe, and the less active one would then just be Cu. So you can see that that's how the answers are lined up here as well. So you just choose the correct answer from that list. Does anybody have any questions? Okay. All right, well, let's go through some of these problems as they appear on the test. I'm actually going to re-roll this so we get other examples of those. Okay. So the questions that relate to Module 6, you'll find them after you see the periodic table and the polyatomic ion sheet here. So you'll have access to that during the test. This looks exactly the same. All right, so now what this does is it puts things together. Let me move this around here. I'll create another page here. Keep that for later. So for this one here, it says consider one of the single ions on the reactant side of the full ionic equation. So there's a lot of homework that relates to this as well. But here, it looks like it's all about the copper, so we have to figure out what's going on with the copper. But if I was to do this, the idea would be to draw pictures of everything. There's only one of those that's going to be relevant though. So if I drew a picture of PtNO3 4, it would be Pt4 plus and 4 NO3 minuses. And for the copper, it'd be 2 Cl minuses and copper 2 plus. Now it's after the single element. So the single elements would be Pt4 plus, NO3 minus, Cu2 plus, and Cl minus. And in this instance, it's pretty clear we're looking for the copper, so the answer there would be copper 2 plus. Anybody got any questions? Okay. So same kind of thing over here with the other examples. And I think there's 6 of them that you would do there. Then, and number 17 is a balancing type exercise. So to balance something like this one, we've got 3 H's on this side. We have 1 here, so I put a 3 in front of the HCl. Then I can put a 3 in front of the NaCl to balance the chlorines. And then I would look at the NAs. The NAs are balanced and the PO4s are balanced. So that one would be balanced at that point. So that would be the sum of coefficients then would be 1 plus 3 plus 3 plus 1, which would be 8. Does anybody have any questions? So then you get a hydrocarbon balancing. Can anybody tell me if we're going to have to multiply by 2 or not during this process? Do you remember what I said? So look at the hydrogens. The hydrogens are 12. Divide that by 2, you get 6. That's an even number. I'm expecting that I'm not going to have to multiply by 2. So I do this, I put a 9 in front of the CO2. I put a 6 in front of the H2O. 9 times 2 is 18, plus 6 is 24, which means I put a 12 in front of the O2 to balance. That would be 1 plus 12 plus 9 plus 6 would be my answer there. So 13 plus 15 is 28 would be the sum of coefficients for that. Does anybody have any questions? So that was my cell phone earlier I was from a student because I can tell by the number. But because my number for the number I give you comes up when I do that. Was it one of you who was trying to call me to tell me something? I'm guessing not. Okay. So number 19, this is where we come up with the compounds for the acid-base reactions. So for something like this, I would definitely want to draw it out. You can see that we know we're getting water, and that's because we get FeOH3 minus, minus, minus. The Fe would be 3 plus. H2SO4, draw that out. So we know it's the Fe3 plus that's joining with the SO42 minus. The H plus and the OH minus, that's what goes together to give water. And it's the Fe3 plus and SO42 minus that we're interested in combination wise, which would be Fe2SO43 would be the answer we'd be looking for. Does anybody have any questions about what we're looking for? We're not even trying to balance the equation. We're just trying to get the compound. Any questions? Okay, that's a similar problem. The next one has to do with the double displacement. And here we're looking for the two products that we're going to get from that. So we go through a similar process to what I just did. It's amazing to me that people think that they can do this without drawing them out, but I think more often than not, people get it wrong and they don't draw it out. I begin to get the idea that they understand what they're doing is they're not drawing it out. So SiO32 minus, again, we get that off the polyatomic ion sheet. So we've got Na plus, Br minus, so Fe3 plus, Br minus, Na plus, SiO32 minus. We know that the Fe3 plus joins with the SiO32 minus, the Na plus joins with the Br minus. So the compounds would be Fe3 plus and SiO32 minus, and Na plus and Br minus. So that gives NaBr as 1, and the other one is Fe2 SiO3 3. That would be the answer we'd be looking for because that's the one that's relevant here. Any questions? That one's similar. Okay. So for something like this, the sum of coefficients of the full Ionic equation. So I give you a balanced reaction. The reaction's balanced, and you can see it does have the solid there as well. And that shows you what's what. But again, it's a matter of being able to come up with the pictures. Now the solid, and this is important, the solid stays whole. We don't split that apart. And the reason is because it's a solid, it forms that precipitate. And then we've got the KNO3s, we've got 3 of those. So that splits into 3 K pluses and 3 NO3 minuses. So if I add up everything here, I'm going to have 4. This would be 4 ions here. This will be 1. And then the 6, this will be 6 for the KNO3s. So the sum of the coefficients then would be 15. So that's a way you can kind of shortcut it a little bit. All you're doing is just drawing out what they split into as ions, knowing that solid doesn't split into ions, and then just adding everything together at the end. So that's how you do that. It's actually not that bad if you do it that way. Does anybody have any questions about that one?
I have a question.
Mm-hmm.
So basically, did you just break it all up and then like add the total, back, like the Al and then the NO3 negative? You got a total of 4 of those together.
Yeah, I just counted them up, Tristan. See,
Okay.
1, 2, 3, 4. Same with the K3PO4. 1, 2, 3, 4.
Okay.
I mean, if you look at it, if you know how, you actually don't even have to do that. If you know what they are, like there's 4 particles. That's 4 particles. That's 1 particle. That's 6. You can just add them together that way. But you'd have to know how they split apart.
Okay.
If you don't know that, then there's no hope.
Would you recommend splitting them up before trying to get the sum of the coefficients?
As long, well, it depends. It depends. If you can look at this and you can tell immediately just by looking at it that it's 6 particles, then it's easy.
Okay. Thank you.
But if you're still not sure about it, then you should split them apart.
All right.
This one is asking for the net ionic equation. And for the net, we're only interested in what's forming the solid. So what I'd like to do for the net is just look at what the solid is. It really is this easy if you look at it. There's your solid. And now what's going to form that solid? Well, we need 2 Fe's and we need 3 CrO4s. We put the charges on there as well. It'd be 2 minus and 3 plus. And the answer would be 2 plus 3 plus 1, which is 6. So really, that's how easy the net is, because you're only interested in what's forming the solid. Look at the solid and look what forms that. So we need 2 ions, 3 chromates, and away we go. So it doesn't have to be that complicated. You can just say, oh yeah, well that's what's forming the solid. The H plus and the Cl minus here end up being spectator ions. So that's why we don't include them. All right, does anybody have any questions? Okay. Decomposition reaction. So we've got HClO3,5. We know it's going to form something with X and Cl minus. The X is going to be 5 plus. And then we'll have O2 as a product as well. And the reaction then will look like this. HClO3,5 gives XCl5 plus O2. The X and Cl are balanced here, but the oxygen, we've got 15, we've got 2. So to balance that, I'll put a 15 in front of the O2 and a 2 in front of the XClO3,5. That will give me a total of 30 oxygens on each side, and then a 2 will go in front of the XCl5. So the answer to that would be 34 if we're looking at some coefficients. Does anybody have any questions? Okay, the last one here is the single displacement reactions. So let me pull this back up again here. So we've got our single displacement, and I told you how we can determine the anion and the cation. And what we know is that if the neutral is more active than the cation, then the reaction goes. If the cation is more active than the neutral, the reaction does not go. In this instance, we know that the reaction is going because it doesn't say no change in the observation. So we don't need you don't need that activity table because we know that the reaction is going or not going from the actual problem. So the answer is yes for this one. There is a reaction. The neutral element, it's going to be Na. The cation, it's going to be the Fe2+. And the more active one, well, we know the reaction's going. So sodium, the Na, the neutral one, must be more active, which means the Fe is going to be the one that's less active. And that would be the answer I would choose out of this list. And that's it. All right, does anybody have any questions? All right, let's take a look at the schedule here. Get an idea of what's going on per the syllabus. All right, so we have Module 6. That's due on October 4th, so that's this Sunday coming. And then we've got the practice test 2 extra credit will close on Tuesday, and test 2 will be due on Wednesday of next week. All right, so that's how this is going down. Remember that the test doesn't have to be done on Wednesday. You can do the test anytime, but the extra credit opportunity will close on Tuesday night at 11:59 p.m. Does anybody have any questions? I'd be interested in your feedback about this. I toyed, I did, when I was setting up the schedule, I did toy with the idea of having a Zoom session last week. But, I guess I'm a bit cynical and jaded these days. Students just don't tend to do, even if I give 2 weeks or something, they tend not to do anything until like 3 days before it's due. It doesn't really matter. I just feel like, well, I can give you the opportunity, but most people don't do anything. That's why I didn't bother doing a Zoom session, because generally students haven't done anything anyway. It's kind of pointless exercise. I'm hoping that you have done something before coming today, because it's that's the assumption that I've made, is that you've done something before coming here. But anyway, just feel free to send me an email. Let me know what your thoughts are about that. And maybe I'll make some changes to this in the future in this kind of instance. All right. Well, if anybody's got any questions, they're more than welcome to stay. If not, then I guess I'll see you around. All right. See you all later.
See you.
Thank you.
Thank you.
No worries.